Okay. Hello, everyone. Thank you, Mr. Chairman. I'm honored to have the chance to address you on this special occasion. The topic of my paper is a blockchain-based consensus slicing mechanism for distributed and SDN control plan. And my name is Shanqing Jiang. Okay. The outline of my talks are as follows. The first part is the background introduction. The second part is the main content of my work. Finally, I will make a simple summary. Okay, let's have an introduction. By decoupling the data forwarding plan and the control plan, logical centralized software-defined network (SDN) has an open and flexible programming interface. The SDN control plan has a global view of the network to facilitate the management of the entire network, such as computing, forwarding passes, and traffic loading balancing. As network scale expands and the application scenarios become increasingly complex, a single controller cannot meet the reliability and the scalability requirements of the network. A single controller faces a single point of failure, and switches located far away will suffer from long response delays, which may result in delayed follow role in installation. Therefore, distributed SDN controllers solve these problems effectively. Multiple physical SDN controllers manage the entire network, dividing network into multiple domains, with each domain's SDN controller responsible for managing a part of the forwarding devices in the data plan. The distributed SDN controllers enhance the robustness and the scalability of the control plan. Physical distribution enables switch to be closer to controllers, which reduces the response delays. However, physically distributed multiple controllers still need to maintain a logically centralized network view to provide correct forwarding decisions for network applications. The physically distributed and logically centralized control plans can be classified as two categories: hierarchical and flat, as you can see. The distributed SDN controller maintain communication between each other through east-west interface to maintain consistency of the global network view and the coordination of control decisions. The consistency of the global view requires various network states in SDN to be synchronized among multiple controllers. Network state includes node topology, flow table, and other information, which together form the network view of SDN, as shown in the figure. The distributed SDN control plane consists of multiple physically distributed controllers, each responsible for managing a part of switches in the data plane. The controller in each domain is responsible for issuing forwarding policies to the switches within the domain, while also updating the local network view of the domain. Controllers between different domains communicate with each other through east-west interfaces, exchanging their respective domains network views and synchronizing to achieve consistency in the global network view. For example, in the figure, when host 1 in domain A wants to communicate with host 2 in domain C, a forwarding path needs to be established between them. Controller A can calculate a forwarding path from the source host to the destination host based on the global network view, which benefits from the real-time synchronization of network state information, such as host location and the network topology among multiple controllers. In fact, maintaining consistency of the network view between multiple controllers is a very complex task. We can consider the synchronization of the network view among distributed SDN controllers as an instance of data synchronization in a distributed system. Therefore, the synchronization of the network view also follows the constraints of the CAP theorem. Its consistency, availability, and partition tolerance cannot be guaranteed simultaneously. Only two of the three can be chosen at the same time while ensuring partition tolerance. Under the premise of ensuring partition tolerance, the synchronization of the global network view faces a trade-off between consistency and availability. Specifically, if consistent is emphasized, network state should be synchronized among multiple controllers before providing access service to the application. If availability is emphasized, the network state should respond to application access requests in a timely manner, even if the network state has not been fully synchronized across the network. Therefore, our goal is to design the optimal network state synchronization strategy. The main work of this paper is introduced below. And we propose a two-stage strongly blocking mechanism to support our work. We figuratively express consensus slicing as a time-sliced synchronization stage of set S, multiple dimensional network states, and set C, basically distributed multiple controller instances in the time dimensions. Each consensus slice includes a series of entities and strategies for achieving consensus, including the objects of consensus is various network states, and the subjects of consensus is multiple controller instances, and the consensus protocol. The consensus nodes the duration of consensus, and the synchronization stage, including synchronization period within the time window. During the time window of the consensus slice, multiple controllers will synchronize the state information according to the slice attributes. Okay, to implement the mechanism of consensus slicing, we designed a framework for collecting and synchronizing network status information in a prototype system, which includes a network states collection model and an application service level agreement (SLA) generation model, and a consensus slice generator, and a multi-chain and distributed database for synchronizing and storing network states. Okay, first we draw in inspiration from the NIB of Onyx and the store mechanism of ONOS, where multiple controllers locally store network data structures within their respective domains. Through interactions and synchronization among controllers, various types of network state across multiple domains are formed into a globally consistent consensus. We firstly analyze these network states and found that they can be classified into 3 dimensions: entity, state, and transaction. For example, the controller, switch, host, and link is aligned to the entity. The topology flow rules is state, and when a node is destroyed or a link is destroyed, this is transaction. The fundamental problem that information consensus need to solve is the consistency of the 3 tuple and other information in the same time and the different space. We have modeled availability and consistency requirements of network applications at a final graduality. We establish a mapping relationship among network application controller network state duration. That is, within a specified time, the network application will require consensus to be formed among multiple controllers for a certain type of network state. The SLA model is established for ensuring the consensus requirement of network applications, such as the formula shown. The fine-grained requirements of specific network applications can ensure that the required network state is confirmed and synchronized among the involved controller, and the data of the state can be returned to the application without waiting for the global consensus among all controller instances. In order to measure the consistency among controllers, we introduce the factor of network states diversity based on the previous analysis. The greater the difference in network states between controllers, the weaker the consistency of the network will be. The cost of maintaining consistency among multiple controllers mainly includes two aspects: the synchronization load of each controller and the synchronization overhead between controllers. We analyze the relationship between these costs and the synchronization parameters. After analyzing the metrics for measuring consistency and cost, it is necessary to find the optimal balance point between them to maximize benefits. The optimization goal can be adjusted by lambda 1 and lambda 2. After completing the generation of consensus slices and the formulation of synchronization strategies, it's necessary to select an operative storage method for the network states information for multi-domain networks. Some data describe network configuration and the device attributes and have characteristics such as low frequency and high importance. In the other hand, other data are real-time network states information with characteristics such as strong real-time performance, large data volume, and tolerance for a certain degree of loss. To address the different characteristics of network states information, we have designed a different storage mechanism that fully leverages the advantages of blockchain and distributed databases. If this type of network snapshot information belongs to real-time large amounts of information, it is stored in the multiple storage nodes of the database. The non-frequency critical information, it is stored in a structured manner in the blockchain, and the data is read and written through smart contracts. Our proposed data hashing mapping mechanism is proposed based on the combination of distributed databases and the blockchain technology to verify whether the data in the database has been tampered. The detailed steps are as follows. Okay, let me introduce the experimental evaluation. The SDN network we generated consists of 20 forwarding network nodes and 7 controller nodes. The network is divided into 4 control areas. To evaluate the correctness and the effectiveness of the proposed strategy, we implement a distributed load balancing application running on top of the controllers. We compared the results of the proposed adjustable consensus slice mechanism with those of the non-adjustable strategy. Under the result shows that under the proposed adaptive strategies, the consistency level is more stable and has no lower overall communication overhead than no adaptive strategies. Compared with other steps, the time for querying the database and computing the hash value is relatively short and is not greatly affected by the number of data packets. The time spent on putting the hash value on the chain fluctuates around 20 ms and is not affected by the number of data packets. The total time consumption of differential storage always falls between that of the blockchain and the database. Like the other two streams, the storage time of this stream also increases with the number of data packets, but the rate of increase is much slower than that of the blockchain. This advantage becomes more obvious as the number of synchronized data packets increase. Let me back a quick summary and conclusion. We innovatively propose a consensus slicing mechanism to address the problem of network state synchronization among multiple controllers. Second, the proposed method minimizes consistency differences between controllers and reduces the performance overhead of network state synchronization. In terms of basic implementation, we utilize a storage method that combines blockchain with distributed databases to store the global network view, improving information storage and query efficiency while ensuring the temporal proofing of data information. And that's all. Thanks for your listening.